In the previous lecture, we have started to discuss the Schrodinger picture, and you have seen that in Schrodinger picture actually the state vector or the state eigenvector Ket psi, or simply you can say psi, is time dependent, but the Hermitian operator a hat associated with a dynamical variable a is not a function of time, and assuming the state vector as a function of time, as you can see here, Ket psi equal to Ket psi of t, and a hat is not equal to a hat of t, we have seen what is the equation of motion in the Schrodinger picture. The equation of motion you have seen actually is simply the time dependent Schrodinger equation, and in case of a stationary state it is simply the time independent Schrodinger equation. Now in this present lecture, our aim is to find the expectation value of an operator in the Schrodinger picture. So we will start from the basic definition of expectation value of an operator, and then we will apply the Schrodinger picture to get the expectation value of the given operator. And in fact the expectation value will be obtained, and after that we will also find the equation of motion in terms of the Hermitian operator, whose expectation value we will calculate in this section. So now let us start to find the expectation value of the operator, let us say a hat. As you know, the expectation value of the operator a hat is defined like this. This is expectation value of as. Here actually I have used the superscript s over a. In fact, this S refers Schrodinger picture. So, in fact, we have to study apart from this Schrodinger picture, two more pictures, that is Heisenberg picture and interaction picture. So, and the same thing will be discussed in the other two pictures too. So, to differentiate the concept of different pictures, I have used here the superscript s. When Heisenberg picture will be used, will be discussed to find the expectation value of the operator, then we will use the superscript h, and in case of interaction picture we will use the superscript I. So to differentiate these things, I have used here the superscript s. So remember, this s refers the word Schrodinger picture. So the basic definition of an expectation value of an operator is like this. In the state let us say psi s, this is defined as bra psi of t as Ket psi s of t over the scalar product of psi s with psi s. But as you know, this state vector psi s is actually a normalized eigenvector. So this scalar product in the denominator will be equal to 1, as you can see here. And so the expectation value of as is simply equal to the scalar product of as Ket psi with this psi s, or you can say bra psi s as Ket psi t. Now, our aim is to find the time derivative of this expectation value of the operator a hat. So, let us operate the operator d dt on this expectation value as. So, d dt as will be what? This is d dt, this much, this is expectation value of as. And as you can see that in case of Schrodinger picture, this operator a hat is not a function of t. So whenever we will differentiate this function, we must have to use the partial derivative, although outside of this bracket you have written d dt, but when you will operate this operator on the particular function, you must use the partial symbol, because we have to treat as independent of t. So you can write this is just a product of two functions. So first of all, we operate this operator on psi. So this is bra del psi del t as and ket psi. Now we will keep the bra psi at each and operate the operator on ket psi. So in this way you get this equation 1 as you can see here. Now this del psi by del t, which appears in our equation, can be obtained from the equation of motion of the Schrodinger picture. When you say equation of motion of the Schrodinger picture, what does it mean? It means the time dependent Schrodinger equation. So we know from time dependent Schrodinger equation. We know this is also called equation of motion. I h bar del psi by del t. I am not writing in ket symbol. This is equal to what? This is, you know, this is equal to h hat psi. And so from here we can easily find the value of del psi by del t. What will be this? You can see this is 1 over I h bar h hat psi. And now we will use this expression, or you can write it as you know 1 over I is equal to minus I. So you can write it minus I over h bar h hat psi. So use this result for del psi by del t in this equation 1. At the place of this del psi by del t, we will write minus I by h bar h hat psi, and also at the place of this del psi by del t, we will use that expression. So using this result in this equation 1, what we will get you can see. So you can say using this in equation 1, you can see d dt expectation value of as. What will be this? You can see the equation 1. Here there is actually bra of del psi by del t, and del psi by del t you can see this is equal to this much. So this is bra minus I over h bar h hat psi, and then there is as ket psi. So this is as ket psi, and plus the second term is bra psi as and ket del psi by del t. And again we will write at the place of del psi by del t minus I over h bar h hat psi. And now let us simplify this result to some extent. As you can see that this factor is at the place of bra vector. So and you know the bra vector is simply the complex conjugate of the Ket vector. So and this I by h bar is a constant factor, so we can take it outside of the bra, and when we will take it outside of this bra operator, then we have to take its complex conjugate, and complex conjugate of minus I will be plus I. So you can write it I over h bar, I over h bar, and bra psi h hat as, and Ket psi, Ket psi, and here there is a factor minus I by h bar, so we take here minus sign. This is minus I over h bar, bra psi as h hat, and Ket psi, Ket psi. You can see this factor. Now we can take this factor I over h bar as a common factor, and so when we will take I over h bar as a common factor, what will be the remaining term? You can see this can be written as bra psi HAS minus ASH H hat, you can write H hat, and Ket psi, Ket psi, Ket psi. You can see. Now, if we take minus 1 as a common factor, it means if we take minus sign outside, then this term will just interchange the sign, then that will be ASH hat minus H hat AS if you take the minus sign outside. So you can write this expression like this: d dt expectation value of AS, and this will be minus I over h bar, minus I over h bar, and bra psi, and interchange the term now. This will be AS H hat minus H hat AS, AS H hat minus H hat AS, H hat AS, and Ket psi. Now you can see what is this. This is just commutator or commutator bracket of the operators AS and H hat. And again, this minus I can be written as 1 over I. So you can write it 1 over I h bar, 1 over I h bar, and commutator of AS and H hat, or you may equivalently also write this 1 over I h bar can be taken outside of this bracket. This can be written as expectation value of the commutator of AS and H hat, AS and H hat. So this d dt AS is equal to this much. This is your equation 2. In fact, this equation is also known as equation of motion in Schrodinger picture in terms of the operator as. So this is also equation of motion. Equation of motion. Now you can see that if this operator as and h hat do not commute, it means as hat and h hat are anti-commute, that is they do not commute, then this commutator will vanish, this will be equal to 0. So you can say that actually this as hat, as comma h hat, what is this? This is actually the commutator of as and h hat, commutator of this. And now one thing is very important here, that if we consider that the operator as does not commute with h hat, then this commutator will be 0, and then this d dt as will be equal to 0. So if as does not commute with h hat, then this commutator as h hat will be 0, and therefore in that condition you can say that this d dt expectation value of as is equal to 0. In fact, there is another situation when this d dt expectation value of as is 0. And what is that condition? If you will consider a system in one of the stationary state of the system, then you will see that this quantity will be again 0. That is, the time rate of change of this operator as will be again 0. You can see it. So this is another remarkable fact. So if you consider that if the system is in one of the stationary states, and let us say, what is that stationary state? Let us say psi equal to psi I, and this is equal to phi I of r times e to the power minus I over h bar EIT. You know, the stationary state of the system may be represented by a state vector like this. Here actually this phi of r is independent of time, and so this function phi of r actually represents the stationary state of the system. So if you consider this stationary state, then let us try to find what will be the value of d dt expectation value of as. So in this condition you will see what will be its value. So to evaluate the value of this d dt as, let us try to find what will be the value of this factor. So if you will calculate the value of this factor, then it will be easy to calculate the value of d dt expectation value of AS. So let us try to find it. See this. Now, first of all, we will find that factor. Instead of psi, now we will write psi I, and AS H hat minus H hat AS and Ket psi I. Our aim is to evaluate this factor, because when we will evaluate this much, you can see directly then this d dt as will be evaluated. So I am just going to evaluate this factor, and I have written at the place of psi this psi I, and psi I has been defined here, you can see. Now see, we will put the value of this psi I here. You can see this is bra phi I of r, or you simply write phi I. There is no need to write r, because it is understood that it is time independent. It is only a function of a space coordinate. So write only phi I times e raised to the power minus I over h bar EIT and AS H hat minus H hat AS and Ket psi I. Again we will write phi I e to the power minus I over h bar EIT. We will write like this. Now you can see this exponential factor is inside the bra vector, bra operator, and this exponential factor is inside the Ket operator. So when we will take it out, that is the exponential factor inside the bra symbol, when it will be taken out, we must have to take its complex conjugate. So what will be that? That will be actually equal to e to the power plus I over h bar EIT and times, and when this Ket when this exponential factor inside the Ket will be taken out, it will remain at ease. So this is simply e raised to the power minus I over h bar EIT. And now the remaining factor is what? This is bra phi I AS H hat minus H hat AS and Ket phi I. Now you can see the product of these two exponential factors will be e to the power 0, because here there is plus power and here is minus power, and powers are same. So this will be e to the power 0, and that will be equal to 1. So you can write it simply. This is bra phi I AS H hat minus H hat AS Ket phi I. And say this is equation 4. Now according to the Schrodinger time independent equation, according to Schrodinger's time independent equation. Time independent equation. We know, in fact, h hat phi I of r equal to ei phi I of r. You know, in fact, this is a stationary state phi I of r, and ei is known as the eigen value of this operator h hat. So here we can see when we will use this result on this equation number 4, what will be our result, you can see easily. In fact, this result can be also written like this. See here, this can be written in this manner. This is in fact, what is the expression? First of all, write this expression and then we will simplify it. So therefore, bra phi I as h hat. Now one thing let us consider here. Take the minus sign outside. Then this negative term will be now positive and this positive term will be negative. So write first of all h hat as, h hat as, and minus as h hat phi I. Now use in this result this Schrodinger time independent equation. You can see when the operator h hat is operated on phi I of r, then we get ei phi I of r. So and in Ket symbol you can write this expression like this: h hat Ket phi I equal to ei Ket phi I. Ket phi. In Ket symbol you may write like this. Now here actually this h hat is operated on the bra vector phi I. So according to this equation we will get what? We will get the complex conjugate of ei and bra phi I. So when h hat will be operated on this, our result will be what? This will be actually equal to what? This will be ei star bra phi I as and minus as, this as. And when h hat will be operated on Ket phi I, see this equation, Schrodinger's time independent equation, you will get simply ei times Ket phi I. Ei times Ket phi I. So now let us see here. This equation, when this minus will be imposed inside the terms in the bracket, then this second term will become plus and the first term will be minus. So this equation you can see may be written as ei minus ei star, ei minus ei star bra phi I as Ket phi I. You can write like this. And therefore you can say I have actually evaluated this term. So what will be this? You can see here. Since the operator h hat is a Hermitian operator, and you know You have already studied Hermitian operator in previous lectures in detail, that the eigenvalues of Hermitian operators are real. So in this case, this EI star will be simply equal to EI. So you can say as eigenvalues of a Hermitian operator are real. So EI will be equal to EI star, and therefore this term will vanish. So I am just writing here 0 sign. You can see, since EI star is equal to EI, so this term will vanish. And if this term will vanish, you can see from this equation that if this is 0, then this d dt expectation value of AS will be equal to 0. So you can say that this d dt AS is equal to 0. So you can see that for a stationary state, the time derivative of expectation value of the operator is equal to 0. And this is also 0 when the operator AS does not commute with H. So these are the two situations when this time derivative of this AS is equal to 0. So this is a very important result and you should remember it. So till now we have actually find the equation of motion in Schrodinger picture in terms of the operator. Particularly we have evaluated the value of the time derivative of the operator, and you have seen that in case of a stationary state of the system, or when the operator does not commute with the with AS, then this d dt AS is equal to 0. Now let us consider that our system is in an external field. So if the system is in an external field, then in fact this operator AS may depend explicitly on time. In fact, when we discuss the system in external magnetic field in atomic and molecular physics, then this idea is vividly used. So now let us consider the another situation, and that another situation is what? Now we are considering that our system is in an external field. That field may be an electric field, or that field may be a magnetic field or electromagnetic field, or simply you can say that our system is in the presence of a perturbing field. Actually, the external field perturbs our system, and in that condition AS it is possible that AS will now depend explicitly on time. So you can say in the presence of an external field, AS may depend explicitly on time. So when AS is an explicit function of time, then what will be our result? Then when we will calculate this derivative d dt expectation value of AS, then what will be our result? you can say that this is d dt, and you know expectation value of as you have already defined earlier, that this is actually Bra-Psi as Ket psi. But now this as is also an explicit function of time. So this as will be also partially differentiated with respect to time t. So in that condition you will write this expression as like this. This is del psi by del t as Ket psi plus. Now we will operate the operator on this as. So this will be Bra-Psi del as by del t and Ket psi. And now we will operate the operator on this Ket psi. So this will be Bra-Psi as del psi by del t. You can see. Now see here. Let us see. First of all, write this term. This is Bra-Psi del as by del t Ket psi and plus. Now see, the sum of the first term and the last term, we have already simplified this expression earlier. You can see here. This is just our term here. You can see equation 1. And we have already simplified this equation 1, and finally you have seen after simplification we get this equation 2. So for the sum of the first and last term, you can write this much from this equation 2. So we can write it like this. This is 1 over I h bar commutator of as h hat. This is actually the expectation value of 1 over I h bar commutator of as h hat. And what is this? Can you say? In fact, this del as by del t is an operator and psi is the state vector. So this first term simply represents the expectation value of this operator del as by del t, because you know according to definition of expectation value of an operator, you can see here that if you define the expectation value of the operator as, then this is like this. So in that equation, simply at the place of as there is del as by del t. So that expression will represent simply the expectation value of this operator del as by del t. So finally we can write this as d dt expectation value of as, and this will be equal to expectation value of del as by del t and plus expectation value of 1 over I h bar commutator of as and Hamiltonian h hat. And this is a most general result or the most general form of equation of motion in terms of the operator. Now you can compare this equation B which we have just obtained with a classical result. In fact, you can remember in the introductory lecture on this quantum dynamics, Actually, I have mentioned some of the equations of motion used in classical mechanics, and we have seen there was actually 5 forms of equation of motion in Newtonian formulation, in Lagrangian formulation, in Hamiltonian formulation, and in Hamilton-Jacobi formulation. Actually, in Hamiltonian formulation, we write the equation of motion in 2 forms, and one of the forms in that case was just identical to this. You can see, as you can remember, in classical mechanics, classical mechanics, for the dynamical variable A. You have seen in the introductory lecture, and you have studied these things in your course on classical mechanics. This is dA by dt. Here A is not operator. In classical mechanics, this is just a dynamical variable. And this dA by dt is written as del A by del t plus the Poisson bracket of A and H. H is Hamiltonian, just like classical quantum mechanics. And let us say this is your equation C. So you can see comparing equation B and C that both are identical. So we can say that comparing equation B and C, we find that the expectation values of the operators obey the same equation of motion in quantum mechanics as the dynamical variables in classical mechanics. You can say, provided we identify the commutator bracket, see here, bracket divided by this IH bar with the quantum mechanical Poisson bracket. In fact, at the place of this Poisson, this is Poisson bracket. In fact, you know, this is Poisson bracket of A and H. I have discussed these things in the introductory lecture. This is Poisson bracket. So in this condition, we can simply say that the Poisson bracket is the classical limit of the expectation value of the commutator bracket divided by IH bar. So it is a very remarkable fact. You can mention it, and for your convenience, I am just writing this thing here. Poisson bracket is the classical limit of the expectation value of the commutator bracket divided by IH bar. Symbolically, we can write the expectation value of the commutator bracket of two Hermitian operators, let us say A hat B. I am writing general here, and when it will be divided by IH bar, then this just corresponds to the Poisson bracket of A and B. Don't write here A hat, but we should write simply A. because in classical mechanics these are dynamical variables, and in quantum mechanics these are operators corresponding to that dynamical variables. So we write here simply A and B. A and B. This is your classical limit. Symbolically you can say. So this is all about the equation of motion in Schrodinger picture in terms of the operator, or you can say the expectation value of the operator in Schrodinger picture. So I hope after the 2 lectures on Schrodinger picture, you have a complete idea of this Schrodinger picture, and in the forthcoming lecture we will see the remaining 2 pictures, and then we will compare and find that in solving a dynamical problem these 3 pictures do not give the different result but they give identical results.